Hello, and let's talk about mathematical operations with complex numbers. Today we're going to learn about, or at least we're going to review complex or imaginary numbers, and we're going to see why they are useful to characterize signals in electric circuits. So the goals are to be able to represent and operate with complex, also called imaginary numbers, or sometimes called complex values. And also we have, from values, we can construct functions that had complex numbers. They're called complex functions. So we're going to learn about those. We're going to learn how to use them, how to characterize them in a mathematical form, and we also want to learn how to characterize signals using polar and rectangular coordinate systems. So as a review, we know that coordinate systems are those that have x and y, or I and j, and they are orthogonal, where they have a value that represents x1 and x2, or y, xy and y will be this point, or if this is called x1 and x2, there are different ways of calling the axis. The point is that a single value here can be characterized with a coordinate in the x, or the horizontal and the vertical direction. Okay, so this is very useful because we can generate slopes, and we can characterize a curve depending on different values. So this is widely used in mathematics. But there's another way of characterizing values, which is with polar coordinates. Polar coordinates is similar, but we use an angle and a magnitude. Okay, so in polar coordinates, we can transform our rectangular coordinate system to our polar coordinate system. Sometimes it's called z, or it's also called r. So the truth is that you can characterize any point by knowing what is the magnitude r and what is the angle theta. So we're going to learn about how to do that and how to transform from one to the other. So the first thing is, what are complex numbers? This is a question mark right here. What are complex numbers? The main the main way to characterize a complex number is in system where this part is called the real part and this is the imaginary part. Complex numbers, by definition, are numbers that have a real part and imaginary part. That is why it's called complex. Now, the imaginary part comes from the term I, also sometimes called j or I, depends on the book. And let's say j, for our purpose, is the same as square root of -1. So obviously this in regular mathematics does not exist, because square root of our number will give you a positive number. For instance, square root of 4 equals 2, because 2 to the 2 is 2 to the second power is equal to 4. So two positive numbers to multiply each other, if you square this number, it will give you 4. So there are no numbers that multiply, negative numbers that multiply by themselves, it will give you a negative number. For example, if you do -2 times -2, this will give you 4. So you can see how you cannot multiply two negative numbers and get a negative number. However, mathematicians said, well, let me just play with this quantity and see what happens. And they say, let's say that j is going to be a complex value where it stands for the square root of -1. So if you let me say that, then apply the regular rules of mathematics to this, where in that case j squared is equal to -1, which again is called complex or imaginary because this in natural real numbers does not exist. You don't have a number, a quantity that are multiplied 2 times will give you -1, right? Because in regular mathematics, again, -1 times -1 is equal to 1. But using complex valued numbers, complex functions, we're going to say from now on, j is going to be a complex number, and j squared is equal to -1. So wherever you say j squared, is like having a -1. There's going to be another rule where is going to be 1 over j is the same as having -j. Okay, so these are the three rules that we need to know for complex numbers. That j is the same thing as square root of -1, that j squared equals to -1, so it's just getting rid of the square root and having j by a power of 2, and then 1 over j equals -j. This is the reciprocal. How you express them is similarly as we said x and y before, where this is x and this is y, x horizontal, y is vertical. Similarly, we said, well, the real component of a number will be in the x direction, and the imaginary component of a number will be in the y direction. In other words, if you have a number complex equals 3 plus j 3, you cannot add them together, because this is, say, 3x and 3y. These are complex numbers. What you do is in your vertical and horizontal numbers, when you have your real component and your imaginary component, you're gonna say, okay, we have 3 here, and we're gonna have +3 here, and where they meet, that is my number. And you can actually find the slope and everything for that number. So the complex conjugate is the inverse of it. So as you see here, this example was c equals 2 parts real, 3 parts imaginary. The complex conjugate is a negative imaginary part. So 2 parts real, but -3 parts imaginary. Okay, so it's just another way of representing a number. Now we're gonna say that we have a real part and a complex part. So how to use those things? It's very easy. You can have the magnitude of the complex number the same way that you use Pythagoras theorem. So if we said, okay, well, if this is my real part, and this is my imaginary part, then I can say, well, in my example before, we had, let's say, 2 plus 3j, or j3, doesn't matter which part you add the j, it's just multiplying. You place the j, what part you place the j is not important as long as explicitly said for this part. In other words, it's the same thing if you say j times 3, then 3 times j. That also depends on the book. Sometimes by convention they decide to put j first, but this is okay. So to find the magnitude of this number, you simply do the magnitude of it by squaring both terms, just as Pythagoras theorem. So 2 squared plus 3 squared. Okay, the square root of 4 plus 9 equals square root of 13. So the magnitude of this complex number is square root of 13, just by using this formula right here. If you want to transform this number from rectangular coordinate systems to polar coordinate systems, then what you need to do is find the radius or the magnitude and the angle. So the angle is found using tangent inverse. So in this case, in our example, the angle is going to be inverse tangent of y, which is 3, and 2, which is x. You compute that in your calculator, and that gives you the angle. So you can represent that number the same way that you did before, with a magnitude, which is z, and an angle, which is theta, based on your tangent -1. Okay. So be careful. This number will give you have to be careful what units you get. So in this particular case, I'm assuming degrees. So this angle is going to be in degrees. So make sure that your calculator is set to degrees. So practice how to do this. there's a function called tangent inverse in your calculator, and you simply do 3 over 2 and apply the tangent function. Now if you want to go from polar to Cartesian, the only thing you have to do is get your x and y components back. So the magnitude times the cosine of theta will give you your x component, and your magnitude times your sine, this is an error here, this is not cosine, is sine of theta is equal to y. Okay, so obviously to go back to x and y on rectangular coordinate system, you need to know your angle and the magnitude. So if you have your complex number in this form, then you can transfer it to polar. If you have already the angle and the magnitude, you can take it back to the rectangular system. So the way you characterize your complex number in the polar coordinate system is the magnitude z, and this little thing that looks like greater than but it's not, it's an angle, and your angle. So complex numbers are very useful, and they opened a whole branch of mathematics that was not even considered before. And one of those things is called fractals, more specifically Mandelbrot fractals. And I'm sure you've heard of fractals before. Fractals are these particular or very interesting objects where if you zoom into the object, you'll see the same object at a reduced scale. Right? It's the concept of if you have, say, a building and you start zooming into the building, instead of seeing bricks, you would see much smaller buildings that form the bigger building. Right? That in real mathematics, real numbers, that is not the case. We know that if you zoom into the building, you'll see bricks, and if you zoom into the bricks, you see atoms. But in this complex imaginary world, fractals form shapes that if you zoom into the shape, you'll see the same shape again, and you can go infinitely, you can go for a long distance into the shape, and it really depends on the scale and the computations that you're able, the amount of computations that you're able to calculate to be able to know how many steps into the fractal you can go. So Mandelbrot was an engineer at IBM, and full disclosure, this was developed once computers were available, because doing computations with complex functions is just not so simple, and we'll see in a few minutes why. Say you have a function that is x plus y squared. This is my function. So function of z equals that, where obviously z is x plus ij. Right? So anytime you give a real and imaginary number, you compute it, do squared those numbers. We'll learn how to do that, because remember, these are not regular numbers, these are orthogonal or perpendicular, so we have to know how to do operations with those. It will be a polynomial operation, and once we compute that, it will give us a complex answer. And Mandelbrot found that depending on the functions, it will build, sometimes it will build a circle, and sometimes it will build a square, and sometimes it will build a function that would tend to go to infinity. So he started to do a map in terms of colors, of if it's very close to the original value, let's say it's blue. If it's very large, say 1,000 times larger, it will be red. And he started to do those things, and when he mapped them on a computer, on a screen, or printed on a paper, he saw that he would get these nice shapes. So these are mathematically complex. These are complex values computed mathematically in a computer, obviously, because you have to do thousands of computations to get this amount of details. And he called them fractals, and he basically meaning that if this is being one of the scales, if you go into any point of this map and zoom in, you will see the same thing again. And there are plenty of videos online. You just Google this and see how they do simulations where they zoom in and they see similar behaviors. Okay, so this is a very interesting field of mathematics. Opened a bunch of branches, and everything started by some mathematicians saying, "Let me just do a game where we say the square root of -1 is a complex number, and we're gonna apply that to the rules of mathematics that we know so far." Okay, so again, this is how to plot in a rectangular coordinate system your complex numbers, and how to plot in a polar coordinate system your complex numbers. Never ever, this is the point I want you to take home, never ever combine your real term with your imaginary term. Real terms are their own world, imaginary terms are their own world, and the only way you can combine them is finding the magnitude of the number by doing the square root of x squared plus y squared. This is the only way you combine them, which is this number z in this particular book. Okay, and z is the magnitude of a vector, which I'm sure you've heard the word vector before, and the rest is computing the angle, which you also know how to do, which is tangent inverse of y divided by x. This y divided by this x. This particular example says that we're dealing with x plus ij, but if they told us, okay, now you're gonna do x minus ij, the only thing you have to do is say, okay, is x and y negative, so it will be a line going down instead of a line going up. Okay, right, so how do you compute stuff with complex numbers? So good thing that calculators can do this for you, but at least understand that this is how you do a complex computation with complex numbers. So if they give us a number, any number that has a real imaginary part, the reciprocal is going to be 1 over that. How to calculate the reciprocal is following this rule: 1 over the number times, you remember this part already. Remember when you had square root and then a denominator that you would have to find the reciprocal this way is similar. The answer is going to be x minus y imaginary divided by x plus y squared imaginary. So this thing, remember, do not combine imaginary things with real things. So this is the same as x divided by x squared plus y squared, this is a number, minus the complex part of y divided by z. Okay, so we started with, this is one important part that is very useful for fractals. Notice how we started with a function that is the real part plus the imaginary part. When the reciprocal, instead of dividing each part, 1 divided by each part, in other words, if you have c equals 2 plus j3, they ask you for the reciprocal and you say 1 divided by 2 plus 1 divided by this. This is not the case. This is wrong. The reciprocal is done like this. It's 1 divided by the complex number times the reciprocal, which is x minus imaginary y divided by x minus imaginary y. Obviously at this point you don't cancel them each other out because you want to compute stuff. So this times that gives you this, and this times that is a polynomial quantity which will give you this. Okay, so that is the same as this. And then if you were to plot this thing, you will have something like this, where is your real part. Actually, let me use another one here. If you were to plot that in a bigger scale, so this is your real and this is your imaginary. So notice that your initial quantity right here was 2 divided by, 2 in the real case and then 3 in the imaginary axis. So this is the line describing that point. Okay, so this is your 2 plus 3j. This is your imaginary, this is your real. Now we have is 2/3. If you go back to this point right here, we have in the real world, in the real axis, you have x, which is 2, divided by z, which is 2 squared plus 3 squared. So this is 9. This is square root of 13. So 2 divided by square root of 13 is going to be a much smaller number. And then it's going to be minus a much smaller number. So it will be over here. Okay, so the reciprocal of this value is a point over here. Okay, so it's not intuitive at all. It's not just dividing each other out, or it's not 1 divided by the real part plus 1 divided by the imaginary part. No, you have to do these sort of computations to get your reciprocal. Again, the calculator can do this, and in fact, if we go to Google Colab, you can open your Google Colab from here, name it whatever name you want, complex nums, and then as long as you don't get rid of the extension, Google Colab will know that it's a Python script. And then you can say that your complex number, capital C, equals, what was it, 2 real plus 3 imaginary. Just by adding j, Python knows that you're dealing with imaginary numbers. If you run this, no errors. If you print C capital and you say yes, and if you say type, it will say yes, it's a class in Python, which is okay, so it's already defined. Okay, good. So if you want to do C inverse, let's call this C inverse, or C reciprocal, equals 1 divided by z, and then we want to print this. Then we're gonna have that is 0.23 minus 0.15 j, right? And that is because if we were doing z equals square root, we're gonna need to color square root functions numpy. So import a numeric package for Python as np, and then we want to do np square root of np point square root of, let me see, am I getting any errors here so far? What is square root of 2? Yeah, I can run that. Excellent. So square root of 2 times 2, which is squared, plus 3 times 3, which is 3 squared, right? 2 times 2 is the same thing as 2 squared, and 3 times 3 is the same thing as 3 squared. So that's going to be my z. If I do a number c computed equals, and then call this real part, and if I say 2 divided by z, and c computed imaginary part, this is going to be 3 times z. What are real and imaginary part. Print z, my c computed, real, and my c computed imaginary. Let me see if I got any errors. So let's see here. This is gonna be 2 divided by z and 3 divided by z. Okay, now if I wanted to do c rec, is 1 over c. So I get this number here, 1 over the reciprocal of this is telling me that it's 0.15 and 0.23. Okay, so if I'm following my PowerPoint here, I'm saying that we should be able to do the reciprocal by doing x. This is a typo here. This should be y. Oh, okay, my bad. I did the wrong thing. I do not need to find the magnitude. It's not the square root of that. Okay, so I already said something that is not true. So the z is not calling z anymore. Let's say denominator. Then denominator is gonna be that and that. If I run it again, I get, there you go. So let's do this again. My complex number equals, or my complex number z equals, it's not z anymore, it's just c as Charlie. So my complex number is 2 plus 3j. Excellent. My reciprocal is 1 over c, so let's do 1 over c equals this. And if I run it again, I get 1 over c equals 0.15 negative 23. So this is to tell you that Python will save you a lot of time and a lot of effort. But just for now, I want to show you how to compute it. Just following this formula. 1 over x squared plus y squared. So what we need to do is x divided by x squared plus y squared is the real part, and the imaginary part, again, I don't understand why this is here. This is another type with y, so this part is correct, but this part is not. This is y divided by x squared plus y squared. So x squared plus y squared is 4 and plus 9, 13, and then if we do the reciprocal is 2, the real part divided by that denominator, and the complex part, or the imaginary part, is the imaginary part divided by the denominator. And by rule of operations is going to be a negative quantity. So this is going to be simply 0.153 real and negative 0.2307 imaginary, which is what we get if we use Python's computations. Okay, so you can use your calculator. Your calculator will definitely do this, or you can use Python in Google Colab. Okay, let's move on to the next one. Also, if by rules of polar and rectangular coordinates, if you want to express this in polar coordinate system, you can simply say the same thing, where 1 divided by z and negative angle. So this z is what I computed earlier. Z equals the square root of x squared plus y squared. Okay? And of course this square root is the whole thing. That is z. And in polar coordinate, the reciprocal of a complex number, otherwise 1 over c. Of course we know by now that c in polar is z and the angle. 1 over c equals 1 over z with a negative angle. Okay? In other words, if you were to plot that, the complex number is, this is c, and an angle. The reciprocal, it will be 1 over c is this point and this angle. Okay, obviously this is going to be shorter than this because it's 1 over z, or longer depending on what the z quantity is. If it's a decimal or if it's a whole number, you just compute it, and that's how you plot it. Now this is how you add numbers. This is very simple. It's real part with real part and complex part with complex part. So if you have two numbers, say 2 plus 3j, and then you have another number which is 4 plus 5j, then the way you add those numbers is real part with real part and complex part with complex part. In other words, 2 plus 4 equals 6 real. Both of them are positive, that's okay. 3 plus 5 equals 8 complex. Okay, and you can do that with Python as well. Generate a new block of code. You're gonna say C1 equals 2 plus 3j, and C2 is going to be 4 plus 5, we said, right? Right. Okay, so let's do a print of C1 plus C2 equals C1 plus C2, and we should be able to get, what is this? 6 plus 8j is what we got here. Okay, this is another example right here. 2 plus 4 and 3 plus 1. For imaginary is 1 imaginary as well, so real with real. 2 and 3 is 5, and 4 and 1 is 5. So 5 real, 5 imaginary, and that is plotted right here. Subtraction is exactly the same. Say if you want to do C1 minus C2, then here you can do, it's going to be pretty simple because it's just changing the signs here, minus and minus. So the first thing was 6 plus 8, and the second one is minus 2 real and negative 2 imaginary. The example here uses 1 and 4, and 4 plus 6. If you want to subtract C1 and C2, then you do 4 minus 1, because this is C1, 4 minus 1, and 6 minus 4. Okay, so this is just the subtraction of both complex numbers. So it's just saying that it could be positive or negative, the number, it could be whatever it is. The only thing that you need to do is make sure that you follow the signs correctly. Again, if you use Python or calculator, you save all this problem of getting an error in the computation. You just get your result by using the calculator, but it's always good to know how to do them in case you need to do it by hand. Multiplying them is a little more complicated, but it's just like any multiplication. You would do for a number that is x1, j, x, so real part is x1 and the imaginary part is x1 as well. So for instance, if we were to do the computation of the multiplication, we would regularly do anything like that. We will do y1 plus y2 and y1 x1 plus x1 times x2 plus y1 times x2 plus j y2 plus x1 here plus j y2 times j y1. So the tricky part here is that you get this j squared, and if you remember from the rules of complex numbers, j squared equals square root is equal to -1. Okay, so j squared is equal to -1. Therefore, this will change its sign. Okay, so for instance, for complex number 1 and complex number 2, you simply apply this rule of x1 plus x1 times x2 minus y1 times y2. And notice that even though these were complex numbers to start with, now they dropped the j because j squared equals -1. So the only thing that happens here is that you will have a negative sign here in front of it, -1. And you do the imaginary part as well, y1 times x2 plus x1 times y2. In complex or in polar coordinates is much simpler. So if you can, my advice is to map those those rectangular coordinate system numbers into polar coordinate system numbers, so that if you notice here, you have a complex number 1 and complex number 2 in polar coordinates. You simply multiply the magnitudes and add the angles. Theta 1 and theta 2, and those angles were found with tangent inverse. Okay, but if you want to do it by hand, I would definitely use the polar coordinate system. If you have Python, simply do what we've been doing here, which is simply multiply C1 times C2 and let Python do everything internally for you, or your calculator. So -7 plus 22j. Okay, so this -7 is precisely because of this -1 right here. So this is an example for you. So a complex number 2 plus 3 and 5 times 10. So let's do this one here, 2 and 3 and 5 and 10. 2 and 3 and 5 and 10. No, 1 0. -20 plus 30, -20 plus 35, and that is what we get here at the very bottom, -20 and 35. Okay, alright, so the way you do that, as we said, is 2 times 5 and -1, 3 times 10, which are the imaginary parts, and then 3 times 5 plus 2 times 10. So if you follow these complex and imaginary numbers, you just follow the rule of thumb, and then you get -10 plus 35, which is the same thing that we got with Python right here. Okay, so division is also a little complicated to do by hand. You can do a lot of mistakes. You just have to follow this formula given two complex numbers, x1 real, x1 imaginary, and x2 real, y2 imaginary. Sorry, this is supposed to be a y, y1 and y2. Then you only have to do is multiply the first complex and the second complex, but with the reciprocal. Notice that this is going to be C1 divided by C2 by the reciprocal of C2. So it's a little complicated. I advise you change them, you map them into polar coordinate systems, where you do the magnitude of the first one divided by the magnitude of the second one, and then you subtract the angles. But you can also use Python to do this for you, or your calculator, and this will give you the answer 0.32 minus 0.004. Okay, excellent. So this it's basically really following the formula. C1 minus divided by C2 is 1 times 4, and 1 times 4 is the real part of C1 and the real part of C2, plus 4 times 5, which is the imaginary part of one and the imaginary part of the second one, divided by the real part of 1 squared, plus, I'm already confusing myself, this is 4, this is this 4, the real part of the second number, plus squared, plus the squared of the second number. I'm following this formula right here. And now this is everything for the real part. The imaginary part is similar. It's 4 times 4, which is the real part of the second number, times the imaginary part of the first number, minus the real part of the first number times the imaginary part of the second number, divided by the same thing, the denominator, which is the real part of the second number squared, plus the imaginary part of the second number squared. So kind of gets a little complicated, and not only you can get mistakes here, but it also takes time. So again, please use your calculator if you can. But even though it's pretty complicated and annoying sometimes to compute the numbers, it's very useful to get the representation of complex numbers in polar form. So if you can, whenever possible, just transfer your real numbers or your complex numbers into polar form. And again, we know that for a complex number x plus jy, you transfer into polar form having z with angle, with z is the square root of x plus y squared, and the angle is tangent inverse of y over x. Okay, so all this is because a wave, if you were to compute every point of the wave, they match certain points on the vertical axis. So like this point represents this point is gonna be here, and it's not easy to know which point is what, mostly if they're shifted by some type of offset. So first of all, if you remember from before, the offset they're shifted is going to be the angle. Okay, so if you're able to represent the complex number mathematically, you're also able to characterize a wave as a set of complex numbers. So in the case of sine wave, for example this wave, were to tell you the voltage 1 has a value of 2 volts sine wave omega t is 2 pi f, remember, and this is going to be times t, which is the time domain. And then they tell you we have a second voltage which is 3 sine omega t, so two guitars connected to the same amplifier or something, so we have two waves, and then you can add them pretty easily if they have the same phase. Notice that they're both starting from the same point. So if you add them, the only thing you have to do is add the magnitudes. That's why I was telling you before that noise builds on top of amplitude, because noise is just waves that are added on the same phase that the waves are created. So adding two waves is pretty simple. If I have the same phase, you just add the magnitudes. So 2 sine omega t plus 3 sine omega t is 2 plus 3, 5, is 5 sine omega t. In polar coordinates is even simpler. You have your value of 2, your value of 3, and if you add them, since they have no offset, the angle is 0, then the answer is 5 volts with no offset. Okay? But careful, because this is just the amplitude, this is just the peak value. this is not, don't think about this voltage being from an appliance or from your um, electrical systems at home, because those are rated with RMS, which we'll see later how to do the root mean square or the average values. This is just an example of how to add voltage waves on top of each other. So this example is pretty much what the example about noise on a wave could be. So another thing is how to calculate the maximums and minimums, and we're gonna get to that point. And if you talk about maximums and minimums, you can think about deriving. You can derive a function, which we'll review how to do derivatives. But this is an interesting thing that if you remember from your calculus, when you derive a sine wave, you get a cosine. But if you remember, we also mentioned that a sine wave is a cosine wave with an offset of theta. So, for instance, if you have V1, a voltage 1, which is 2 sine omega t, but then you have a second voltage that has an offset. In this case, both of them cannot be added so easily. In fact, if I give you the answer, it's not intuitive at all, because it's telling you that it's not 2 plus 4 anymore, because there's an offset. It's 4.5. How do you get that 4.5? Well, we actually know how to get it. I'll show you. And one is 0 offset, the other one is 90 degrees offset. How come the resultant is 63 degrees? Well, in polar coordinates, it's very easy to see why. If you were to plot both waves, you get that one has 0 offset and it's 2 volts. The other one has 90 degrees offset and it's 4 volts. And z is the square root of both of them, so square root of 4 squared plus 2 squared, or 16 plus 4, and that will give you this number. Okay, so we also know how to calculate the angle, because the angle is tangent inverse of y over x, and y is 4 and x is 2. So if you compute this, 4 over 2, which is 2, in tangent inverse, you're going to get 63.43 degrees. So the total is 4.47 sine of omega t plus the offset angle, the resultant. Of course, they're just saying the 447, they're going to approximate to 4.5. Let's do another example. So in this case, they're giving us the current 1 is 5 sine omega t at a 30 degrees offset, and there's a second current at a amplitude of 6 amps in sine of omega t at a 60 degrees offset. So if you want to add them together, it's going to be pretty simple. If saying that this is the magnitude of the amplitude, you can say, okay, 5 amps at 30 degrees and 6 amps at 60 degrees. You just basically add them together, as we saw. Is 5 plus 6 and 30 and 60 degrees. Now, in polar coordinates, it's very easy to multiply and divide, but in rectangular coordinates is much easier to add and subtract. So to add them, let's go back to rectangular coordinate system, and you know that the way you do this is that a complex number is x plus jy, where x equals x equals z cosine theta, y equals z sine theta. If you go back and do z, for the first one is 5 times cosine of 30 degrees. this will give you this number, 4.33. In fact, we can go, if you don't have a calculator, we can go to cosine of 30 degrees times 5 equals 4.33. Okay, so that is gonna be my x number, which is right here, over here, and y is y equals 5 times sine of 30. So my sine of this will give you 2.5. Can you do the same thing for complex number 2? So there's going to be, we already found for the first complex number. We'll do the same for the second. This is going to be 6 cosine 60, and this is 6 sine 60. And once you have those, we simply do real plus real and imaginary plus imaginary, and you can see that 2.5 plus 5.2 is 7.7, and 4.33 plus 3 is 7.33. Okay, so this is the summation of both waves, and then you can take this back to your polar form, where z equals square root of 7.33 squared plus 7.7 squared, square root of that, which will give you 1063, and then the angle is tangent inverse of y over x. So the sum of both waves is 10.63 sine of omega t plus 46.41 degrees. Okay. Which is right here. So if you were to do that in conventional mathematics by using sines, this is going to be pretty complicated. Because if you notice, these are continuous values. So you have to do like almost every point, and it's, every point of the wave together. It's pretty complicated. Versus with polar coordinate systems, is just straightforward. So remember, for multiplying quantities, use polar coordinate systems. For dividing quantities, use polar coordinate systems. For adding and subtracting, use the rectangular form. And you know how to go back and forth using the square root of x and y and the cosine and sine of the magnitudes. So just as we said, time domain to phasor domain. Phasor domain is pretty much how we say the polar coordinate of the wave. So just one more time, in case you don't remember x and y, being that this is imaginary, you can take it to polars by saying z and angle. Okay, but to compute the RMS, now we're talking about the root mean square, the average value is with, and we'll talk about this in a few minutes. I'm going to tell you this straightforward computation, and I'm going to tell you why in a minute. The RMS is times a square root of 2, or 1.41, which is the same thing. And since this is with 0 degrees offset, then we have no offset here to worry about, no angle to worry about. But if you have your z of 50 volts, for instance, if you want to take it back to your time domain and find the RMS value, it's going to be 50 times square root of 2. If you have, for instance, 69.6 sine omega t at a 72 degrees offset, then in terms of phasor domain or our polar coordinate system, you would have to do 1 divided by square root of 2, and 1 divided by square root of 2 is, so square root of 2, let's do square root of 2, square root of 2 equals, and 1 divided 1.41 equals 0.707. So if you do this in your calculator with all the numbers, it will give you 7.707. In fact, let's do this a little better. 1 divided square root of 2. Close. There you go. This is 0.707. So this is why we're doing for phasor domain is 1 divided square root of 2. In time domain is 1 times square root of 2. So in other words, if we want to take a quantity, say, what do we have here? Square root of 2 times 50. To phasor domain, we'll multiply by 1 over square root of 2. That's why we get rid of the square root of 2. If we have another example here, for instance, say 69.6 sine omega t plus 72 degrees. We know that the 72 degrees is going to be already at the angle for the phasor. This is the angle for the phasor, 72, and then it's going to be our 69.9 divided by square root of 2, which is same as multiplying by 0.707. So practice that. This is an example. Write the expression for the following phasors at 60 Hertz. So this is going to be the common electricity wave signal or power signal going to house in US at 60 Hertz. So they're telling you that the current is 10 angle 30, phasor 30, and we know that we have to do 10 to the time domain is 10 times square root of 2 times sine of omega t, so 2 pi f, which is 60 Hertz, 60 times t plus 30 degrees, which is right here. And doing that computation, you get 10 times 1.41 is 14.14 sine of 317 t plus 30. So this is the RMS value of the wave. Okay. Now similarly, notice that if they give you in a polar form 115 volts or 115, it's voltage, phasor negative 70 degrees offset. So in time domain, that is going to be, as we know, square root of 2. I'm not able to write, times 115, and sine of 2 pi frequency, so 2 pi times 60, and pi is a number, 2 is a number, 60 obviously is a number, so you do that computation is 377 at negative 70 degrees. Okay, that goes here. There's another example right here. So they tell you find the input voltage of the following circuit in series. So as you know, voltage in series is basically additive. So this is a good example of how noise is built up. And they give you that the voltage at source A is 50 sine of 377 t. So for the example before this, meaning that we're operating at 60 Hertz and it has a 30 degree offset. And then they tell us that the second voltage is 30 volts sine of 377 t 60 degrees offset, and this is because it's 2 pi times 60. This computation gives you 377, around 369 point something, and you can round up to 377. So to find the total voltage, because we're talking about a circuit in series, we simply have to add them, and we know how to add them by now. So if you take the time domain wave into a phasor domain wave, you know that you simply have to take your 50 and divide it by square root or multiply by 0.707, and that gives you 35.35, and the offset angle is 30. Okay, and the voltage for signal B is 30 times 0.707, which is 2121, and has an offset of 60 degrees. As we saw before, it's simpler if you transfer those polar coordinates into rectangular coordinates, and we can do that by saying the x component is z, or 35.35 times cosine of 30, and sine is j, 35.35 sine of 30. So that should give you 30.61. Please use your calculator and make sure you get the same numbers to practice this kind of computations. And the complex part is 17.68. If you do the same thing for the complex number 2, or for the voltage through the component B, you should have that 21.21 cosine of 60 gives you 10.61, and 21.21, which is the amplitude right here, which this 21.21 is because of the time domain voltage after we get the RMS, which we'll talk about RMS in detail, how to get RMS and why we use RMS. Then the Y component is 21.21 sine of 60. Now it's very easy to add these two together, because the only thing we have to do is, once we have those two numbers, just do the real part and real part here, and the imaginary part here. So 30.61 plus 10.61 gives you the real part, and 1768 plus 1837 gives you the imaginary part. And those two things together give you 41.22 and 36.05. Of course, you can take that back to your polar form, and your polar form is going to be the magnitude, which is 41.22 squared plus 3605 squared. All that is square root of these components. That is going to give you 54.76, and you know that the angle is tangent inverse of y over x. That should give you 41.71. If you want to take that back to the time domain and plot it, the only thing you have to do is, again, do the RMS computation, and it will give you square root of 2 times z, which is 54.76, of 2 pi f, which is 2 pi times 60t, plus your angle, which is 41.17. And this is the wave that you obtain after adding them together. Now this is another example. So if you notice, the question here is pretty similar. They give you the input voltage, the input current. They give you one of the currents, and they're asking you to determine which one is the second one. So like this one is in parallel, and we can do that very easily as well, because we know that currents in parallel just add each other. So we can do that by saying that I2 is I total minus I1, and I total is 120 milliamps sine omega t of 60 degrees offset, and I1 is 80 milliamps sine of omega t with no offset. So as we did before, we find the polar representation by multiplying 120 milliamps by 0.07 or divided by square root of 2, and the same thing for I. We're finding I total and I1, so we have the polar representation of both. We can get the real and imaginary parts of both quantities, and in fact, once we have both real and imaginary quantities, we just do I2 is I total minus I1, and we do real part minus real part, and imaginary part minus imaginary part, which in this case this is 0, so it's simply going to be the imaginary part for this first number. When we get the answer, we're going to do the square root of both terms. It's going to be a positive number because we're doing square power. We're doing the second power of each number. So 14, negative 14, 14 times negative 14, 14 is going to give us a positive number. And once we find z, we simply take it back to the polar form, and we find our theta based on tangent inverse of y over x. Then to take it back to the time domain, we simply multiply these by square root of 2, and we add the opposite angle, which this is the answer. Okay, so if you were to plot them together, we would get 105 is right here. Let me see, this is I2, right? So this is the wave that we just found, 105.8. So we know by now how to add waves with different phases. And as I told you before, it's important to know the maximums and the minimums because of the peak voltages that are definitely going to ruin our components. To know the maximums and minimums, we can find the derivatives. And it's pretty interesting that in a circuit, the derivative of the voltage times a constant, not any constant, but a pretty important constant, will give you its current. So the constant we're talking about, C, comes from the capacitance, which we'll see in a few moments how to add and how to use capacitance the capacitance in a circuit. So given a wave that in this case is sine wave with no offset because it starts from 0, we know that the maximum of that voltage is going to be when the derivative is equal to 0. And of course, since this is a wave, is symmetric, then the minimum is going to be the same value but inverse on the negative value. So the derivative equals to 0 will give you the minimum as well. The maximum is when it's crossing the time or the horizontal axis. So at this point, it gives you the maximum value of the voltage, which can be computed with dV dt as well. So the derivative of the voltage function with respect to time gives us the maximums and the minimums. And why can we do that? Because if you remember, all this time we said that we had a function that it was omega t. This t is a variable, and this t is what we're using to derive the function with respect to. Okay? So the current and voltage across the capacitors have the same frequency and period. This is a very important rule of thumb. So, for example, if you say that you have a wave with frequency 1 that also you encounter another wave with frequency 2, but frequency 1 is greater than frequency 2, then the voltage, the difference in the voltage with respect to time, will give you a higher value for the higher frequency. Okay, that's why short range waves have higher power, carry higher power than long waves. For instance, Bluetooth has a lot of power in the short term, in short distances, because it has higher frequency than an AM radio. But of course, this short frequency wave, the Bluetooth, cannot travel a long distance. So in fact, if you have your Bluetooth, if you have your phone in the kitchen and you go to your room, you might get some noise in there. Versus radio, you can have the station in a different city and you can still listen to the radio sometimes. So even though the power is higher, the distance traveled is less. So a review also, the derivative of a sine wave is cosine, but be careful with the arguments. So say a constant, as long as this is a coefficient and not a function, so a coefficient multiplying sine omega t of plus minus a phase, the derivative of that function is omega times cosine. Obviously the constant stays the same, omega t, and the same sign that the phase had. And remember, omega is 2 pi f, so it will be, in our previous case when omega was 377, it will be 377 times the or voltage or the power that the sine or the wave carries. So again, the derivative of a sine wave is cosine. For example, if we talk about a sine wave going through a resistor, the voltage might diminish because of the resistance, but the phase stays the same. So there's no change in offset. The wave carries the same phase. So it's basically a reduction in the amplitude. Okay, so it's, if you had certain power after going through a wire or some type of resistance or the air, the amplitude is less, but the phase is exactly the same. So this is very important when we start talking to about impedance and reactance and all those things. Sine waves going through through resistors have the same phase but different amplitudes, usually reduced the amplitude. So for example, the voltage across a resistor, we have to find the expression after going through a 10 ohm resistor. So for the example being 100 sine of 377t and 25 sine 377t plus 60 degrees offset. So in the first case we have our sine wave, and it's 10 sine 377t, and the resistance is 10. So we know by Ohm's law that V equals IR. Since they're asking for the voltage across and they want us to find the current, so the current for V and I, we already have V but we don't have I, so I equals V divided by R. So 100 volts divided by 10 ohms gives us 10 ohms, right? 100 divided by 10 equals 10. And since there's no phase difference, the only thing we have to do is just pretty much draw our 10 sine 377t with no offset. So this new curve is 10 sine of 377t. This original curve is this one, 100 and sine 377t. Okay, so it's very simple. When a wave goes across through a resistor, the only thing that changes is the amplitude. So just basically take, if it's current or voltage, be careful, follow Ohm's rule, and you should be able to only manipulate the amplitude. But when there is, in the case of a wave with offset, remember the wave can have an offset, but going through the resistor does not add or decrease the offset. So this part stays the same. The only thing that varies is this. So 25 divided by 10 ohms is going to be 2.5. So the new wave is the same input wave without a smaller amplitude, in sketch right here. When we talk about inductors, and this is an example about inductors, but I want to go in details about inductors because transformers and a lot of other stuff use magnetism for motors, to use magnetism to operate. So we'll go in more detail about what inductors are, but right now I'm introducing concepts that we'll be learning in a few days. So the voltage through a conductor is the derivative of the current in time times the inductance, and this is a value that manufacturers will give you or that you can find on tables. So if the input current is some initial current times sine omega t, the voltage will be the inductance times the current times 2 pi frequency, which is omega, cosine omega t, because the derivative of sine is cosine. Okay, so for example, in a case where they give you a voltage and a current, the reactance, inductance, the reactance of the inductor, which is expressed with capital XL, inductance, is omega L, which is right here. And this is because after you derive your function, you get omega Lim, so you get this part right here that we just computed, omega Lim, but by Ohm's law you divide V equals IR, so by Ohm's law is V equals IR. If you want to find your R, you do your V divided by I, so I and I cancel out, and you get with your omega L. So your reactance by the inductor is 2 pi f times the inductance. This is a very interesting scenario because if you think about it, you've learned about derivatives in calculus, but this is the physical representation of our derivative in the world. It's basically a wave traveling to a inductor or a magnetic field. By a wave traveling through an inductor, the wave is derived, and you can see it here on the plot. That is basically, first of all, there's an offset of 90 degrees. If you notice here, your answer of after you derive the function is going to be cosine of omega t. But if you remember, there's a trigonometric function where cosine of omega t equals sine of omega t plus 90 degrees. So in order to plot them, we can just simply plot a sine wave with the new amplitude and an offset of 90 degrees. So let's do an example very quickly. So the current through an inductor is 0.1 henries. Henries are units of inductance. So find the expression for the voltage and sketch V and I, the voltage and the current. So A, 10 sine of 377 t, t is time, and B, the current is 7 amps sine of 377, negative 70 degrees offset. So the first thing we want to do, we don't want to do this whole thing again to find the derivative. We just apply the formula to save time. And we know that the reactance, because of the inductor, is 2 pi f L, which we already know is 377, and L is 0.1 henries. So radians times seconds times henries gives you ohms. So that computation of omega L gives you 37.7 ohms. And then by finding the voltage, you simply do the Ohm's law. But in DC circuits, Ohm's law is V equals IR. In AC circuits, Ohm's law is V equals I times reactance, also known as X. So the reactance of a resistor, or the reactance of an inductor, or the reactance of a capacitor. Okay, so in this case, we want to find the voltage because they gave us the current, and the voltage is going to be the current, which of course the current is given by the wave. In example A is 10, and the reactance is 37.7. So in this particular case, the voltage is 377 volts. So if they give you your current, you just need to remember that the voltage equals L dit, and the derivative of sine is cosine, but cosine is equal to sine with an offset. So if you notice, this original function that they gave you is the same one as the voltage that we computed, 377, with the sine of omega t with an offset of 90. It's pretty simple. Now for case B, they're telling us the same thing. They want us to find V and I, but there's an offset, and in this particular case an inductor does vary the offset of the input wave. It's not like a resistor that does not change the offset. An inductor does change the offset. So let's do the same thing. We already know how to compute the the reactance is the same because it has nothing to do with the input amplitude. We know this omega L, and since it's 377 is omega, L is the same, 0.1 henries, so it's 37.7. But then what we want to do now is find the voltage of the new current, which is 7, and the reactance is 37.7. This gives us 263. So if you remember, we're going to do 363 volts sine omega t and plus 90, but there's an offset. So this will give you positive 20. And when you plot it, it will simply be the new wave at an offset of 70. Remember, negative 70 is to the right. Okay. So you plot your original wave, which is the current. The current is right here. And then when you plot it, you have to know that your voltage has an offset, positive, meaning to the left, of 90 degrees. So that will put you at 20. So this is the voltage. 263 volts with a current of 7 amps. So this example right here is pretty close to real world applications. This could be a small compressor or a small motor operating a little higher voltage than usual. Well, yeah, this is actually a pretty good example because it's not the RMS voltage, it's the actual whole amplitude. So this could be a voltage of 264 volts and a 7 amp motor, which are very common for many applications. Another application that we can use complex numbers for are the capacitors. So as we saw before, the inductance of inductor, or the reactance of an inductor, is omega times L. The reactance of a capacitor is 1 divided by omega C. Why? Because if you remember, the current through a capacitor equals the capacitance times the change in voltage with time. So if you have a voltage with a sine wave and you do the derivative of that, you're going to get, of course, all the constants multiplying out, 2 pi f times the capacitance times the voltage, but you get a cosine function. And if you remember, the cosine function is a sine function plus 90 degrees opposite. So when you apply the rule of Ohm's rule, you're going to know that V equals I times reactance, in this case of capacitor. If you want to know what the capacitance is V divided by I, and Vm divided by I, which is all this. Vm divides Vm, and then you have 1 omega c, 1 divided by omega c. So when you want to plot your voltage, it's obviously going to be from this result right here. So you're going to have your input voltage, which is Vm sine omega t, but when you get your current, when they ask you to plot the current, it's going to be sine omega t with an offset of 90 degrees. So let's see an example. The current through a capacitor is 100 because the unit of current is amps, so I know I was not reading the problem correctly. They're telling me that there's a current going through a 100 microfarad capacitor. So be careful with the units. This is 100 times 10 to the negative 6 farads. And they're giving us the current, 40 sine 500t at a 60 degrees offset. Find the expression for the voltage across the capacitor. So we don't have to do the whole thing again. We know that from before, we know that the current is the derivative of voltage with respect to time. So in this case, the only thing we need to do is find the current through the capacitor, and this given the voltage across. Oh, I'm sorry, I said it again. They give us the current, and what we need to find is the expression for the voltage across it. So we find the reactance because of the capacitance, which is 1 divided by omega c, and we know that omega is this number right here, because if you remember, omega t is the argument for my sine function. Capacitance is 100 times 10 to the negative 6. If you compute this number, it gives you 20 ohms. And the voltage is simply the current. Remember Ohm's law, V equals IR, but in AC we talk about reactance, in this case of the capacitor. So that is going to be voltage. The current is 40 amps and the reactance is 20 ohms. So that gives us a total of 800 volts. So we don't have to do the derivative, we don't have to do anything, we already have the voltage, and we can simply apply the time domain function of sine, which is 800 sine of omega t, and then we apply the rule of thumb of 60 minus 90 degrees lagging. Okay, so let me see something here. Yes, there's a typo in this particular case. We have, this is not plus, but this is minus. So this is minus 90. So I apologize. We have, and I know that because the rule of thumb is that when you have an inductor, you do plus omega t plus 90. You know, of course I'm talking about sine omega t plus 90. When you have a capacitor, you do sine omega t minus 90 and your phase. So in this case, my phase was 60 and then minus 90 because it's a capacitor. Then the answer is 800. If we were to do the answer is 800 sine t, sine omega t minus 60 minus 30 is minus 60 minus 90 is minus 30. So the answer is 800 sine of 500t minus 30 degrees.